Good morning, everyone. Welcome to WESTalks, and this is probably our last month of WESTalks. So, thanks for supporting us all this year long. And uh, so, yeah, just to give an introduction on WESTalks for people who are joining for the first time or who are not that familiar. WESTalks is a joint collaboration between IC Impacts and UBC Future Waters. So IC Impacts is a pan-Canada, Canada-Indian research center of excellence working in the area of water, infrastructure, and health. And UBC Future Waters is a UBC Excellence Center primarily focused in interdisciplinary research at intersection of law, policy, and governance, along with applied and biophysical sciences. So this is the organizing committee of WESTalks. Abhishek, Lady, myself, and Carl are based out of UBC. We have Jaskaran from the University of Guelph and Fedia from IC Impacts, who helps us with all the events. So we are now at May 20th with Dr. Bas's talk today. And moving forward, we'll also have a few more talks before we wrap up West. So we'll keep you updated with our progress. This is the global outreach of our WESTalks, and as you see, we have audiences from all across the globe. So thank you so much for supporting us all this time. And in case you have missed any of our previous talks, you can always access them at the IC Impacts YouTube page. So all our recordings are available there. And just moving before I make the introduction to let you know all about the West Conference. So the West Conference is happening on June 9th to 11th. It's a student-led conference. There's no registration fee. So if you are interested, you can go to the link here and register. And there are a lot of interesting talks from a diverse group of audiences from all across the world, again, in areas of water governance, treatment technology, water reuse, wash, and all other things. So if you're interested, please get in touch with either one of us, or you can go to the website and register. And one more thing, IC Impacts has also launched a student journal paper award, which is the first time they have taken such an initiative. So I would just like to let everyone know that if you're eligible, please submit any of your papers, and there are 3 awards of Canadian dollars of 1,000 plus an IC Impact citation. The deadline to submit is June 15th. And if you want to know more on eligibility, the details can be found on IC Impact's page. If you are not an HQP or have not worked on any of our previous projects, you can always collaborate. So these awards would be offered every year from now. So in case you're planning to apply for something next year, you can get in touch with any of our ongoing projects or ongoing students who are working, and you can be eligible for these awards moving forward as well. So with this, I would like to introduce today's speaker, Dr. Bas. So Dr. Bas is an environmental engineer and earth system scientist by training, is interested in sources, behavior, and environmental footprints of large-scale waste streams. His research aims to quantify the environmental impacts of anthropogenic pollutants by studying their occurrence and transport and transformation processes in natural and industrial context. Dr. Bas uses an interdisciplinary combination of concepts from environmental biogeochemistry, hydrology, analytical chemistry, civil and environmental engineering. So with that, I would like to welcome Dr. Bas, and we look forward to your talk, Dr. Bas.
That's great. Thank you so much, Fuhar. And yeah, thank you very much for having me. It's a real pleasure. I'm going to try and share my screen. I hope this goes well. Yeah, so I'm gonna just get this out of the way, I guess. And yeah, I'll be presenting for the next 30 minutes or so, pretty high level overview of our work on trace metals in the Great Lakes. I see one of my students, Tatiana, is also in the audience, so great to see. It will be pretty high level, so not a lot of technical details. Of course, I'm happy to talk about those kind of things after the talk. And much of this is still work in progress, so just to keep that in the back, I guess. All right, so the Great Lakes, I learned you have well, there's at least one person that I know that is from the area, so they will probably know what I'm going to say in the next couple of slides, but just for those of you in the audience who are international, some context on the Great Lakes. This is probably my favorite spot, the Sleeping Giant Provincial Park on the north shore of Lake Superior. The Great Lakes are beautiful. Whether you're in the upper lakes, the remote areas in the wilderness, or even where we are in Kingston, on the other extreme end of the Great Lakes, beautiful waters, beautiful landscapes. But the Great Lakes, of course, are not just beautiful; they're also really important from a variety of perspectives. It's the largest single freshwater source on Earth, so it contains about 20% of the accessible surface freshwater reserve. We have 40 million people living in the catchment area in the basin, about 10 million of those on the Canadian side, so that's approximately 30% of the population. And of course, the Great Lakes are very, very important, not just for drinking water, but also for irrigation, agriculture, transport, recreation, and a variety of other things as well. Now, the Great Lakes are under stress, and they have been for several decades, I guess more than 100 years actually. That is due to the fact that we have increasing urbanization in the basin. So a couple of really large urban areas, Toronto, Detroit, Cleveland. But even in the upper lakes, we have spots that are under stress. And this map from the Canadian Geographic illustrates that. The stress in this case is kind of an aggregate index for a variety of criteria. So ecological, invasive species, water quantity, so flooding potential, but also water quality, climate change, and so on and so forth. So you can see upper lakes generally a bit more pristine, but severe stress in the lower Great Lakes. And my group is mainly concerned with water quality. So threats, or I would say stressors on the water quality side of things in the Great Lakes are many. We have excess nutrients inputs, so a lot of phosphate coming in from agricultural runoff that leads to algal blooms. You can see this example here in Lake Erie. We had severe algal blooms 2019, 2011. So yeah, severe deterioration of water quality in many areas. Of course, growing urbanization. So this is an example of the growth of the GTA, the Greater Toronto Area. And we are, of course, at quite northern latitudes. So a lot of application of road salts leads to salinification. It's a trend that has been going on for several decades now as well. And we also have a lot of different point sources for contamination, including with organic contaminants, solvents, but also heavy metals. Those are kind of addressed in a policy plan tackling these so-called areas of concern. So throughout the Great Lakes Basin, we have a lot of areas of concern where there is historic contamination, for instance, with metals. One example, for instance, is the Hamilton Harbor here in the far west side of Lake Ontario. So because we have so many different threats to water quality in the Great Lakes Basin, the lakes in general are very heavily monitored and managed as well. The dominant water quality parameters, though, include mainly physical parameters such as temperature and turbidity, and nutrients and major ions like chloride, right? The emphasis has really been on those kind of what I would call standard water quality criteria. We have a lot of offshore and nearshore cruises. So government agencies, they go on periodical cruises, take surface water samples or samples at depth. We have extensive monitoring of tributaries, for instance, through the Provincial Water Quality Monitoring Network in Ontario, and of course, intense monitoring in the contaminated areas of concern. And the organizations involved are quite diverse. In principle, transnational, so both on the Canadian and US sides, through the Great Lakes Water Quality Agreement, we have involvement of 8 US states and the Canadian province of Ontario, Environment Canada, US EPA, NOAA, and a variety of regions and conservation authorities that are also active in monitoring those water quality criteria. Now, so a lot of is done, and a lot has been done in the past, but again, most of that has been on major water quality criteria. And as you will see in the next couple of slides, the situation for metals and even trace metals is quite different. We don't have the same quality of data available to us in the basin. Now, scientists and engineers, I guess we in general we never have enough data, right? But I hope that I will be able to convince you of the fact that this is quite true for metals and trace metals in the Great Lakes. In this graph, I have an overview of data availability for major connecting channels in Lake Ontario. We have hydrometric data pretty consistently available on a very high resolution over the past decades. We have pretty good data on major ions and nutrients, as I said before, but you can see that the available water quality data on metals and trace metals is quite patchy. On top of that, the locations at which these parameters are measured, they change, not just the location, but also the resolution or the frequency with which these locations are sampled, because governments change over decades. They have different priorities, different budgets. Environmental surveillance is also very expensive. So we're talking about hundreds of millions of dollars across the basin, and metals and trace metals are not very straightforward to measure. So again, the relatively little trace metal data that we have is not as consistent across the basin, and especially not on decadal timescales. So despite that we have this history of pollution with heavy metals and increasingly with trace metals as well, the efforts have really focused so far on the areas that we know are contaminated, the areas of concern, but we have little insights beyond those sites. So if we talk about the large scale loads and the large scale dynamics of trace metals in the basin, we know relatively little. So sources on a larger scale, especially diffuse sources, are very poorly known, and long-term trends are not as well understood. And this is true, I think, for heavy metals like copper and nickel and zinc that you probably have heard about. It's also true for emerging, I would say, trace metals, more obscure metals, platinum group elements, rare earth elements that are very tricky to measure because they're present at very low levels. But these elements and metals are increasingly used in our society, right? In iPhones or in the chemical industry. So we really need to do a better job, I think, in trying to get a grip quantitatively on what's happening with these metals in the basin. So that's where we come in. Overarching, our goal would be to try and quantify human imprints on metal and trace metal occurrence in the Great Lakes. So for that, we need to start by establishing baseline, I would say, basin scale understanding of metal behavior in the Great Lakes. So in this talk, I'm going to start with that first, setting up mass balance models for metals. And then second, I'm going to talk about our approach where we use wastewater as a large-scale proxy for human activity. So we can screen for metals in wastewater and see if we can compare that to our baseline understanding of metal behavior to assess on a very rough level the human imprints on trace metal occurrence. So let's start with the first item. And the approach we're taking is a kind of an environmental systems approach, where we look at the different Great Lakes as individual systems, but also as a connected system. So what's unique about the Great Lakes is that they are a series of hydraulically connected lakes. They're all connected through each other through these connecting channels. The lakes are in a relatively close state, so the annual outflow is less than 1% of the total water within the system. So we can have a look at the 5 big lakes all together, but we can also approach each individual lake as a system, in our case, a black box. So we're going to look at the mass of water and the mass of metals in each lake as a function of different inputs and outputs, right? We have a reservoir, which is the lake volume itself. We have various processes that bring in water and metals to the lake. So we have atmospheric deposition, connecting channel flow. We have sedimentation, evaporation, and so on and so forth. So by looking at these individual processes, we're going to take a top-down approach. We're going to see how many of those processes we can quantify based on the available data. And we're basically calculating loads for as many of these processes as possible by looking at water fluxes as well as concentration data, right? So volume per time multiplied by mass per volume gives you mass per time. I hope that's pretty straightforward. So for this, we used an incredible amount of data. First of all, hydrometric data, that is flow rate and discharge data, also precipitation, evaporation from a variety of sources. And our approach was such that we took stations as close as possible to the lake boundaries, as to kind of box in the lakes as much as possible. So we looked at connecting channels, about 100 tributaries, and because the data, the hydrometric data, is available on a very high, almost daily resolution, we have over 200,000 data points between 1980 and 2020. Water quality data, so concentrations of chloride or heavy metals like copper and zinc, is a bit less, less frequently measured, but still available. So through the US, Water Quality Portal, Environment Canada's monitoring programs, and some provincial and state programs, we were able to get over 20,000 water quality data points between the same time period for stations that are very proximate to the flow rate stations that I talked about before, so that we have both hydrometric and flow rate data from the same location, allowing us to calculate loads for the individual components in the mass balance. And on top of that, we also looked at sedimentation and atmospheric deposition estimates, for which we have at least semi-quantitative estimates in the basin. And then what you can do after you've quantified and calculated the loads for the different tributaries and the different lakes across the basin, you can kind of rank which mass balance components are important factors for the budgets of these elements in the lakes. And I've provided two examples on this slide. So we have the top frame here, the Great Lakes loading rates for chloride. So we have atmospheric deposition coming in from the top, tributary inputs as a total of all the tributaries coming in from the bottom, and then connecting channel flow. And you can see that as we move from upstream in Lake Superior to downstream in the basin, we aggregate mass. So there's an accumulation of chloride as we move through the basin, kind of in line with the map you saw before of stress in the basin. So this is something that's been quite well known. Of course, the lower lakes are more, there's more urban development in the catchment area. So we expect that accumulation of chloride, which is conservative, of course, in the basin. For copper, the situation is a bit different. We have relatively higher proportions or higher contributions of atmospheric deposition as well as tributary inputs. And the accumulation is mainly taking place before we reach the lower lakes. So the sourcing obviously is quite different for this particular metal. And we can, of course, calculate similar pictures for other metals as well. Now, this is on a very large scale, but we can, of course, zoom in a bit and have a look at individual lakes and what the tributaries carry in terms of mass introduced to the lakes. And that's an example of that is here on this map. So we have Lake Ontario, the lowermost lake, and copper tributary loads between 1980 and 2020 illustrated. So you can again see that the connecting channels, the Niagara River here in the south and the St. Lawrence, are the major controlling factors. Generally speaking, the lower lakes are more dominated by connecting channel flow, but we can also almost rank the different tributaries that we looked at in terms of their contribution to the copper budget, right? And by doing this, we can highlight or we can identify which tributary systems, which watersheds contribute most to the mass balance of a particular metal in each of the individual lakes. So we saw that annual loads are surprisingly constant over the past 4 decades. So not a lot of temporal variability, which you also wouldn't expect, as the development, I guess, kind of occurs gradually. But they were spatially, at least, very variable between the different metals. So this picture would look completely different for lead or for nickel or any other element, really. So illustrating, I guess, the point that there is completely different sources for these different metals across the basin. And to zoom in even further, on the next slide or two, I'm going to present 2 examples of tributary loads and the effect that they have on particular mass balances in the lake. So the first example is the GTA, the Greater Toronto Area. There are 4 major tributary rivers draining into Lake Ontario: the Don, Humber, Etobicoke, and Credit River. And they basically flow through the big urban area that comprises Toronto as well. And basically what we see is that these 4 rivers combined, they input a total of 2% of the hydraulic budget to Lake Ontario. But when we look at the chloride loads that they carry, they actually carry about 11% of all the chloride that's being introduced to Lake Ontario. So these 4 urban rivers have a 5 times as high contribution of chloride to Lake Ontario as you would expect based on their water fluxes. So carrying really disproportionately large loads of chloride. And this is something, of course, that people have seen in the past. It's mainly due to road salt application. So just for context, the city of Toronto applies approximately 130,000 tons of road salt each winter. So we're talking about very, very high masses. I'll talk a bit more about road salt when we get to the wastewater later on. The other example is the Spanish River. So we're right now we're up in Lake Huron, connecting the North Channel actually of Lake Huron, and the Spanish and its tributary, the Vermilion River, basically drain the area northwest of Sudbury, and Sudbury is of course the nickel capital of Canada and probably the world. So when we do a similar comparison, we see that the Spanish and Vermilion River, they carry about 5% of the water that's entering Lake Huron, but about 30% actually of all the nickel that's entering Lake Huron. So it's a really dominant, a very substantial factor in the budget of nickel in Lake Huron. In fact, the Spanish River alone introduces more nickel than the St. Mary's and the Straits of Mackinac introduced from Lake Superior and Lake Michigan. So a very, very disproportionate contribution. Interestingly enough, water quality limits are generally not surpassed. So even though from a regulatory perspective, everything's fine, the loading rate that's caused by this river is really disproportionate, right? And we are figuring out ways how to, I would say, isolate the geogenic versus anthropogenic component in this load. Obviously, there's a lot of nickel mining and refining in the Sudbury area, but we also have naturally occurring nickel that's not been mined. And through looking at isotopic signatures and more upstream mass balancing, we can separate ultimately the contribution of nickel coming directly from these mining activities versus what is the background nickel load introduced to the lake. So finally, it's kind of put the cherry on the pie for these kind of mass balance estimates. We did some dynamic modeling. So this is the only kind of mathy slide I have in the presentation. Basically, what we did is we expressed the mass balance approach in mathematical form, 2 differential equations. The first one that says that the change in volume of water over time is governed by a combination of inputs and outputs. So similar to the graph I showed before, inputs being connecting channel, precipitation, and so on and so forth. And then a second differential equation for concentration over time. So multiplying flow rates with concentration, and then another couple factors for dilution and sedimentation, and so on and so forth. It's not really important to go into all the details. Basically, what we did is we integrated those 2 in a model environment for water and variety of metals or other elements at the same time. So integrating about 2 million data points on a daily time step to kind of see if we can reproduce long-term water quality trends using our inputted water quality data. And so first of all, I think it's important to illustrate that we were able to reproduce lake water levels. So we want to make sure that we capture accurately the amount of water coming in and going out of each of the lake systems, kind of a quality check for our modeling efforts. And I think that works quite well. So we have going upstream to downstream, Superior, Michigan, Huron, Erie, and Ontario. We're about a meter and a half off, which is, the worst case scenario. Like if that's the worst case, I think it's a pretty good job considering the volume of the lakes that are like 10 to the power of 12 cubic meters. So relatively low errors, reproduction of the seasonal variability as well as long-term trends. So I hope that confirms that our quantitatively the reproduction, I guess, of the water fluxes is accurate. So the next step is then to couple that to the water quality data, tie in the measured concentrations, and see if we can reproduce water quality trends. And that works quite well, especially for the conservative elements. So in this graph, we have chloride levels measured and simulated. And for chloride, which is of course a conservative element, highly soluble, lake-wide concentrations are pretty homogeneous. So, within Lake Huron, for instance, you'd have relatively comparable chloride rates throughout. So that makes it easier for us to reproduce the long-term trends. For metals, the situation is a bit different. It's not as easy, and we are not able to do as well of a good job, but still reasonably okay, right? So this is a simulation for copper. I should put the disclaimer there that these axes are logarithmic, so the error is substantially higher, mainly because the metal concentrations for copper and nickel and zinc are not as homogeneous as they are for chloride, right? So we have differences in offshore versus nearshore water quality, and that makes our black box approach a little less valid. On the other hand, long-term trends, they are reasonably well reproduced. So I think that kind of confirms that on decadal timescales, looking at the entire catchment areas, an approach like this still works quite well. Another interesting feature is, of course, that metals are biogeochemically reactive, so we have to account for things like uptake and absorption. Sedimentation becomes really important for these elements. Of course, not the case for chloride. So those are factors that we can, of course, tie into our models and then use the outcomes of the simulations to quantify these processes in more detail. So what else are we simulating? Looking at contributions of individual tributaries. We're now in the process of trying to tackle even data poor elements. So these ultra trace elements, platinum, rare earth elements, and other technology critical elements. And we're playing around a bit with predicting future water quality trends on a variety of climate change scenarios. So because we directly use hydrometric data on flow rates, we can say, oh, maybe by 2050 or 2100, we might expect 5 or 10% increase in flow rate, and we can see what will happen to the water quality in the different lakes. Okay, so work in progress, right? For the last 10 minutes or so, I'm going to switch gears a bit and talk about wastewater. So very kind of trivial statement, I guess. Wastewater is a mirror of society, which is, I think, very true. We know that people monitor pharmaceuticals in wastewater, microplastics. Since about a year and a half, we've read in the news a lot about COVID monitoring in sewage, which is another good example of wastewater being a reflectance of our society. So we asked ourselves the question, is metal or trace metal use in society also reflected in wastewater loads? Kind of a spin-off of a project I worked on in Switzerland a couple of years ago, where we asked ourselves similar questions in Switzerland. So in the Great Lakes work that we're doing, we're basically trying to see if we can use wastewater as a screening target to quantify or explore the potential environmental impacts at different scales. So at individual tributaries, at individual lakes, or across the entire basin. So we can use a similar black box approach where we have individually crossed off and checked off the different processes, and we now add in another potential source term, which is wastewater effluent, and we are trying to see how much of the water quality, or in this case outflow, is represented by the input through wastewater. So what we've done last year is collected a bunch of samples from facilities throughout the basin, different times of years, pretty much a geographically well-distributed selection of facilities of different sizes, major facilities in Hamilton, Kalamazoo, Toledo, even smaller ones, small lagoon systems. Sault Ste. Marie is on the map here as well. So, of course, we couldn't do this ourselves because of COVID. And instead, what we did is we were a very good customer to FedEx. We shipped a lot of boxes out to all the facilities, or not all of the, a selection of facilities in the basin. We got a very high response rate, so people were eager to send us some samples. We basically packed an instruction sheet and a couple of flasks and bottles in these little packages that we send around, and prepaid slip for the return shipment, and that worked quite well. So we got our hands on about 70 locations, digested sludge samples, so post-treatment, those are about 3-month aggregates, and effluent samples, so samples of the clean treated water that's being discharged into the rivers and or lakes. So on a very rough level, what you can do once you have the samples is you basically, you can measure the elements directly, you can process the sludges and measure the whole periodic system on an ISO-PMS without relatively little effort. So that's what we did. Selection of those results is here. Major elements in the effluent, calcium, sulfur, strontium, and then trace metals. We have another 20 or so elements with even lower concentrations, but just to show you that the distribution, I guess, is very different, of course, between the locations, and also quite different depending on the time of year. You can do the same thing for the sludges. So we measure all the different metal and other element concentrations in the sludges. And yeah, wide variety of concentrations as you would expect with measuring the whole periodic system, right? It's basically, to a large part, in line with what you would expect based on natural abundance patterns, but there are some exceptions, as we will see, we'll see later. So once you have all that data, you can do a lot of things with it, right? You can look at elimination rates, you can calculate per capita fluxes to see, you know, how much, I don't know, gadolinium or holmium does an average person release. You can look at spatial distribution patterns to see if there are any anomalies. Luckily for all these facilities, we know a lot about their capacity, sewer sheds, connected population equivalents. So I'm just going to give you a couple of examples of things we saw. So at the basis of all of that is getting a good grip on what the sewer shed actually looks like, right? Where is the basin that you draw wastewater from? And that can be quite erratic. So this is an example of a sewer shed in the Sudbury area. It's imperative that you know this very well. And of course, it's hard to kind of aggregate all that data for the whatever 600 treatment plants that there are in the basin. So it took us quite a while to figure all that out and to write all the jurisdictions and people to get our hands on that data. But you can then look at geospatial attributes in those sewer sheds and see if there are any correlations. For instance, between chloride loads, so total of effluent and sludge, with road density in the catchment area, right? So in this case, lane length, kilometers of road per square kilometers of area. And there's a very high or very statistically significant correlation, I think. That is something that kind of confirms, you know, the fact that a lot of chloride is introduced through road salt application. Similar studies other studies have found similar results, also for sewer sheds, but also, of course, for watersheds and lakes. So that's pretty like kicking in an open door. But there are other more exotic examples, one of which is gadolinium. So that's a rare earth element. We see a pretty good correlation between total gadolinium coming through the sewage plants and the number of hospital beds within each sewer shed. Gadolinium is used as is used in contrast agents that are used in MRI scanners. And these compounds are very, very stable, which is, of course, what you want when you get the contrast agent injected. You don't want your body to absorb it. The downside of it is that wastewater treatment plants also don't break down these compounds. So they basically flow through the facility without being degraded. And yeah, looking at the number of hospital beds in some of these sewer sheds is a good indication that a lot of the gadolinium that we see being released in the basin is coming from hospital applications. So the total hospital-derived load in the basin would be about 1,000 kilograms per year, which is, it's quite a lot. In fact, proportionally, it's in line with what we've seen in Switzerland, where in our study a couple of years ago, we saw that over 80% of all the gadolinium leaving the country was also from hospital and healthcare sources. So zooming out a bit, doing it the other way around, we also looked, of course, to larger scale, so watersheds. We're comparing effluent loads with riverine loads on a watershed scale. So two examples of that here. The Grand River watershed in southern Ontario on the left, and the Thames River watershed, also southern Ontario, on the right. And basically this map shows you the river and different sub-tributaries, with in green the facilities that we have sampled, and in red the ones we don't have samples for. But basically we can extrapolate whatever we measured on the green ones and see, kind of in the same way that we've done for the mass balances I talked about before, contrast how much of the water versus how much of a particular metal is coming from wastewater facilities versus from natural runoff and other base flow, basically. You can see that for copper and for various other metals, the wastewater derived contribution is much higher than the water derived. So again, disproportionate inputs of metals coming from wastewater facilities in these watersheds. We're of course further looking at these loading rates at the points of discharge. Some of you might know that a lot of the legislation in Canada on discharge regulation is actually based on these dilution factors. So it's a nice way to kind of check that. And then finally, of course, at a very large scale, we can have a look and see what the expected effect of the wastewater derived inputs would be when we look across the entire basin. And extrapolating all wastewater treatment plant effluent discharges, we would end up with about 220 cubic meters per second. So only about 0.3% of the total natural runoff in the system, which is, it's surprising. It surprised me actually that it's still that much. For some metals, nickel and copper, the contributions are higher, which is interesting. Kind of a reflection, I guess, of the fact that these elements are enriched in wastewater, but not to an extreme extent, right? For some metals that we know that anthropogenic uses form a large constituent, the contribution is in fact pretty much the same as for water. So some more work to be done there. We are collecting new data for more obscure trace metals such as gadolinium to kind of fill in the gaps and construct similar analyses. We're also looking at using isotopes and speciation analyses to kind of further solidify these speculated source tracking analyses we've been doing, and looking at seasonal variability to see if these contributions change depending on the prevailing weather conditions or seasons. So I think what all of that shows is, if we use a data-driven approach, we can quantify baselines for metal loads at basin scales, at tributary scales as well, and even on individual sewer shed scales. We can identify major controls on lake-wide budgets. So we saw that even small tributaries can have disproportionate effects. Wastewater treatment plants can be useful indicators of elemental footprints. For instance, if we look at per capita loads and if we want to explain some of these anomalies, so combining them with geospatial analyses, we can identify sources and start exploring some of the risks that we might expect from these metals. We're hoping that this will help government agents, other planners to prioritize surveillance efforts. We need a lot more data on metals and trace metals throughout the basin. I think this approach would be very useful for other contaminants, microplastics, PFAS, pharmaceuticals, just to get a large-scale bird's eye view on where the sources are, and of course paves the way for effect-based monitoring to improve management. Technology-wise, there is large-scale screenings can help us look at the efficacy of metal removal, reduce discharge, look at the mechanisms during treatment. A lot of that stuff is unknown as well. So a lot of stuff to be done for us in the next couple of years. I think that's pretty much it. I would like to acknowledge funding, NSERC, CFI, Queen's University, collaborators at the BD Water Center and Environment Canada, my excellent grad students, Jacob, Tassiani, and Colton. And thank you for your attention.